Hey guys, welcome back to another RESK Maths tutorial, and in this video I'm going to be talking about a clever way we can expand the domain of natural log using complex numbers. So if you don't know what the natural log function is, you might be a bit confused, but it's just natural log of x is the same thing as log base e of x. So if you don't know what log function is, it's basically the inverse of exponentiation. So, for example, we know e to the 1 is equal to e. Actually, is that a good example? Yeah, that's fine. Okay, so we know e to the 1 is e. And if we take logs of both sides, or lns of both sides, like so. And let me just put a ln over here. Then that's going to tell us that ln of e is equal to 1. So you can see what we kind of did here was, we know that e to the 1 is equal to e, so ln of e is going to be 1. We're basically finding what power we need to raise to e, what power we need to raise e to get this number here. And usually, if you look at the graph of this function, this is only defined for numbers which are greater than 0. So not for 0 because it's approaching negative infinity, but this function does approach infinity just super slow, so there's no asymptotes, no horizontal asymptotes. It has a root at 1 because ln of 1 is equal to 0 because e to the 0 is equal to 1. And yeah, this function isn't actually defined for anything in a negative space at all, because if you try and take ln of -5, right, that's the same as asking e to the what power equals -5. And if you know a thing or two about powers, you'll know that this cannot happen, at least not in the real world. If you have like -100 here, that's not going to give you a negative number, because e to the -100 is the same thing as 1 over e to the 100. So it's still going to give you a positive number. So that's why this ln function isn't defined at all for negative values. However, we can actually extend this domain to have the negative side with the use of complex numbers in Euler's formula. So if you guys don't remember what Euler's formula is, let me just write it here. It essentially allows us to connect real numbers and complex numbers. So if I have, okay, I'm going to draw an Argand diagram. This has an imaginary plane and a real plane. And any number, this can represent any complex number. So over here, this might be 4 plus 3i. So this complex number would be 4 plus 3i. If we have just 7, that would be somewhere over here, and that would just be known as 7. And same thing, if we have -1, this, I know it's not scale, but that's just essentially going to be over here on a real line, because -1 doesn't have any imaginary parts. So the way we can figure out how to represent this number in polar form, which is how Euler's formula works, is essentially we need to look at the magnitude of the number and the angle it makes with this horizontal. So if we wanted to represent -1 in polar form, this would be e, since the magnitude is 1, so I'll just write 1 here. 1 times e to the I multiplied by the angle, which it makes in radians, is 180 degrees, which is the same as pi. So that is how you represent -1. So what I'm saying is e to the pi I equals -1. And some of you might know that this is also Euler's identity, e to the I pi -1 equals 0. So this is how we represent -1 as in polar form as a complex number. And now what we can do is, if we want to take the natural log of -1, we can replace this with the polar form, e to the I pi. Use our log laws, we know we can take the power down there. So this is the same as I pi times ln e which this, as we saw earlier, evaluated a 1. So this is just I pi. So there we go. We've managed to take the natural log of a negative number, and it does come out to a complex number. Obviously, it would be a bit weird if it came out to a real number, but it comes out to a complex number. And with this, using 1 as the base unit, we can actually work out what natural log of any negative number is. Like if we had -3, using log laws, we can separate that into ln of 3 plus ln of -1, because if you add two logs, you effectively multiply them. And then we just have ln of 3, which is a real number, plus ln of -1, which is I pi. So there we go. If we have a, let's just say, any negative ln, we just define k to be less than 0. That's the same thing as ln of k plus I pi. So you can see here that the complex part of the negative ln is always the same, and the only thing that changes is the real part. So that means this is symmetrical in, one sec, let me try and draw this a bit better. Yeah, that's good enough. So what that means is, if we just imagine this plane being 3D, like so, and let's just say if we go back, that is a line, this is the imaginary line, and let's just say this point is pi. So this like sort of new ln for negative numbers is the same thing as the original ln, except it's just in a different plane, because it has this complex part of I pi. But other than that, it's basically the same thing. So I thought that was interesting, how we can extend the ln definition, and it does work for all calculations. You need to be a bit careful, but this should tie up with all the rules of maths and things. So I just thought it was interesting how we could take the ln of a minus number. Thanks for watching, and I'll see you guys in a future tutorial. Bye.